Okay, just gonna go through this last one here, and I've already got work done here, so this will go a little bit faster. Okay, our goal in this problem is to find horizontal and vertical tangents. Okay, horizontals are found when dy d theta equals a 0. So I do the computations in here. Oh, by the way, I have to make sure I set these up. Okay, using x equals r cosine theta, put in f of theta, which is 1 minus sine theta. And then you have these two new functions, x and y, in parametric form. Okay, so once we have that, we can calculate our dy d theta. I do so, set it to 0, solve it. I've got several values here. I'm not going to go any further than 3 pi over 2. I mean, you could throw in another one here if you wanted, you know, the 5 pi over 2, etc. But no need to. So got that done. Okay, now I found some others here too. When 1 minus 2 sine theta is 0, we've got these, which continue on. Then I'm checking the dx d theta. And that's going to be dx d theta. Again, using my x that I found up there, my parametric form, I find my derivatives, and I set to 0. And now this one took a little doing because I had to do some substitution in here with some trig, with the trig identity, the Pythagorean identity, put that in, rearrange things, got a quadratic here, and was able to factor it. Got two solutions from each. Okay, or this one, I stopped at pi over 2. I didn't want to go past 2 pi over 2. I didn't think it was necessary. It might have been, but okay. So then I able to get a very rough picture here, and I put in a few values of theta. I put 0. Remember, our curve is it's 1 minus sine theta. So r is 1 minus sine theta. So you can see when theta is 0, we get a 1. So we're out here. Okay, maybe pi over 4. You have 1 minus with 2 over 2, which is about 0.3 roughly. So already, if that's 1, and this is 1 out here, then at pi over 4, it's already back down into this region in here, about 1/3 of that, about here. And mine's very rough. Okay, very rough graph. Come on, baby, there you go. Okay, so then once I continue up this way, and by the time I get to pi over 2, so I cut right to the chase, I get 1 minus 1 is a 0. So I'm back here at the pole. Okay, and if I continue into that second quadrant, with my 2 pi over 3, I'll have 1 minus root 3 over 2. Okay, so that's about in here, about there. And then, actually that one's more like right about there, coming up that way. And this one mirrors this one on this side. Okay, that mirrors this one when I get to pi over 4. Okay, so we're about there. And then when I get to pi, I've got 1 minus 0. So I'm all the way out here. Okay, so now I'm going to take a leap of faith here, since it's moving so slowly. I've tried 3 pi over 2, and I have 1 minus a negative 1, which is 2. So that's down here. Okay, so if that was 1, 1, 2, 3, then 1, 2, 3, 1, 2. Actually, I guess it's a little farther out, isn't it? That was my 1, so I should be more like down here then. So this kind of came out this way. It's a little bigger than I anticipated there. Okay, so this part was too small. Okay, no. So I got a 2 there, and then eventually it starts to shrink back down. If you do some more, put some more points on here, like say 5 pi over 4, you get that 1 plus 2 over 2, which is about, about 1.7 something, right? So it starts to shrink back down, and eventually you get back to that 1. At 2 pi, we have again 1 minus 0, which is the 1. Okay? Now, so that's just, brute force graphing, okay? Without memorizing anything, just brute force graphing. Now, what did we see here? Horizontal tangents. Now, I made a double check. I noticed that this was the same as this number. And the theory tells us that anything can happen when that happens. In other words, this one is saying there's a horizontal tangent or a vertical tangent, and this one is saying that there's a horizontal tangent. You can't have both. So typically what happens at a point like that is that you get a cusp of some sort. And that's what actually happened here. At pi over 2, that's the point, there is a cusp. Okay, now it's coming in from the top down to a point. So the horizontal tangent is heading to become a vertical tangent. Okay, that's what it's saying in a sense. And the vertical tangent wants to be a horizontal, I guess you could say. It's sort of tipping in there. It doesn't know what to do, according to our definition. So it's neither. But these others, 3 pi over 2, that's down here, there is a horizontal tangent. You can see that. Now, I would imagine this 5 pi over 2 would duplicate itself over here eventually. 3 pi over 2, and I'm sorry, 5 pi over 2 would be the same as this one, and there'd be nothing there. Okay, so now as to these vertical tangents, where are they here? These two here. One of them is occurring at 7 pi over 6, that's over here. There's a vertical tangent right there. And there's another one at 11 pi over 6, that's over here on this side. So it's coming in, my drawing's a little rough there. But you should have a horizontal tangent right in there. Okay. I'm sorry, did I say horizontal? I meant vertical tangent. It's a vertical tangent right in there. Okay, now, let's see. I still got these over here to talk about. Those are my horizontal tangents. I got ones right about here. Right there, you see a horizontal tangent come through. 5 pi over 6 is over here. There's another one right there. And then 13 pi over 6, that was going past 2 pi. That duplicates this one here. So we don't need to look at that. But there they are. 3 horizontals, 2 verticals. Okay. I'm going to mention one more thing about this derivative thing. We have done a lot with this dr d theta. I mean, we've been checking dy dx, which gives us the change in y divided by the change in x. And the rate of change of y with respect to x. But what's the rate of change of r with respect to theta? That's a strange quantity graphically. What it means is, let me show you an example. If you had a graph like this, and let's say it was one of those rose curves and it was coming out like this, and it may be coming back in like this, maybe doing something like that. coming back in. Okay, this point out here, R is coming along here. This is R. It moves from point to point. You have a different R value. There's R1, R2, etc. When you find dr d theta, okay, theta's in here. Here's theta 1, here's theta 2. Okay, so if you're finding how R is changing as theta is changing, okay, theta is changing, how does R change? Well, it helps to see right out here on the end the significance of a zero. What does that mean to have a zero? It means that when you get out to this tip out here, that the radii are not changing very much. You get right to the tip there, and the radii before and after that tip aren't much different. The fact is, the change is becoming so small that you can't tell the difference when you get to the tip. And right at the tip, you have a change in radius with respect to theta, as theta is changing, is a zero. And that's where you it's kind of the equivalent of maxing out. But in a sense, if you were trying to find points that were on the graph that were the maximum distance from the pole, this is where you would look. Maximum distance from the pole. But for our purposes, we see that these coincide with a zero derivative when you get out to a point where, with respect to the pole, there's a smoothness to it, and it's just sort of swinging back again. Okay, maxes out, and then it starts to change at a faster rate out there. So we don't really use it the way we did before. We're not seeing that same, and there's really no significance to this anyway. Graphically, we don't have a context for it. So what does it mean to have to be the farthest away from the pole? Max, with regard to maxes and mins. But that's where they would occur if you needed to know them. So anyway, just wanted to mention that because we don't really pay much attention to this guy, dr d theta. In our work, we're always interested in dy d theta and dx d theta and dy dx. This one doesn't really have, by itself, doesn't really show up in our computations as being meaningful in any way.